We'll just wait for a few minutes and then start. In the meantime, if you guys have any questions, feel free to ask me.
Good evening, sir.
Yeah, hi. Yes.
Sir, I have a doubt.
Yeah, go ahead.
Sir, during submission of assessment, my code has passed all the test cases, but still getting 0 marks.
Oh, okay. If you have any questions regarding the submission of assignments and related things, please reach out to PMRF. Sorry, I'm so sorry. NPTEL support. I'm just the TA through the PMRF side. I just take live sessions. I uh, have no. For me, providing support for this won't be possible. Sorry about that. We should have access to the NPTEL support, I'm assuming.
Sir, I had sent a lot of mails, but
Okay.
didn't get response.
You can try asking in the forum also. There is a forum, maybe they'll reach out. There's someone who handles the forum separately. So you can try asking because there are other TAs who handle the coursework, sorry, the assignment part of it. So they make the questions and so on and so forth. So yeah,
Okay, thank you, sir.
yeah. Okay, let's start. So last week we saw about dynamic cast, where you're sort of relying on typecasting. Okay, but the check for it. So let's say you use static cast and dynamic cast. So the main difference is that check happens at compilation time for static casting, and it's runtime for dynamic cast. Okay, right. It's essentially like static cast. Okay. So yeah, this is the example we took. We have integer long and double, and then let's say there are pointers to it. Okay. So you can typecast the pointer, void pointers, okay, dynamically at two integer and double like respectively. Okay, right. So moving on to templates. Okay, in general, the idea behind it. So first of all, the motivation comes from writing the same function for different outputs and inputs. So essentially, it's like your body of the function does not change, just that your input type changes and the return type also accordingly, right? So in this case, instead of writing the same function many times, okay, you can take advantage of templates. You can do the same thing with a macro where you're comparing with, we took example of max functions, right? So you are comparing two numbers and returning the larger one. So this can be done through a macro. Again, the nice thing about a macro is that at least you don't have to do it for every uh, data type. If the data type is supported, okay, you'll get, if it's supported, it's fine to compile it. But if it's not, then having the comparison operator will throw a comparison error. Okay. So there it is, at least the macro is useful in cases like this. Yeah, but for function ways, you have to write for each data type you want to support. You want to support for. Okay. So hence comes into picture templates. So writing a function like this, where you templatize the type, data type itself with let's say T, and that data type itself becomes the type for the input and the output. Okay. Now here the return body where the comparison happens remains the same. Okay. Specifically, now because this comparison happens for uh, data types A, between A and B, T, which is the data type of this inputs, that should support the comparison. Okay, so this is essentially the idea. And since we'll be just dealing with integer, the built-in data types like integer and double, so this is good, good to go. Okay. So as an example, we take integers A and B to compare, okay, and double P and Q to compare. So the actual syntax looks something like this, where you take the max function, you take the integer as the template parameter, which you are essentially telling to the function that here my T is integer, okay, and I'm taking A and B as the inputs. So just an extra uh, addition to normal functions where you just have, let's say, the max and then the brackets. The extra syntax is having these angular brackets and inside it some parameter. Okay, very similar to the integer case, we have the double where we're passing the P and Q, which are double, okay, and we want the comparison to happen for among these also. The extra thing you can do with templates is that you need not always pass the template parameter. While being explicit is always good, certain times you do not want to pass it, as in just to have shorthand representation. So because A and B are integers, it knows which definition to actually call. Okay. So in particularly this case, integer template is not necessary to be written explicitly. Okay. Similarly, with the case for double, you do not need to write it but in particular. Okay. Right. Yeah. So these are two examples, right? Another thing is you can even store it in some value. So I can store A and B, which were um, integers, right? I can store the output in a double. Nothing wrong with that. Okay. Because the return will be an integer, right? But there will be an implicit typecasting because the right hand side is integer, left hand side is a double. Okay. So the rules of typecasting that we have seen so far also still apply to this templatized functions. Okay. Similarly here, right hand side is a double. Okay. The return type of P and Q will with this function will return a double. The left hand side is an integer. So n will take a double and store it in the form of integer. That's the idea here. Okay. Now, an important thing about templates is this function in particular does not exist. Okay. It only has meaning if we provide an actual template. Otherwise, in the memory, if you think about it, a max function with a certain t, let's say integer, if it actually gets called, okay, then only it exists. Otherwise, it doesn't. So it's very useful in saving memory also, because if your code is actually not using any of these templatized functions, then you don't actually need to compile for all of them. Okay. Here it was integer and double. Okay. There could have been for float or unsigned integer, a long unsigned, or any of the other cases. But only integer and double will be um, uh, uh, for those two cases only it will get compiled. Okay. So yeah, that's it. If I comment the double versions like line 18 and 21, only the integer version will get compiled. Okay. So there will exist a max function, but specialized to integer. Okay. So another thing you can do, it's called explicit specialization, where let me take this max function and a specific case of it, let's say integer. Okay. I'm going to write it this way. So to say that uh, I'm not taking any template particularly, but for this instance of max, I want to use this body. So next time when the integer version gets called, it does not use this version, okay? Because we have explicitly specialized this um, template, okay? So it will use this version of it, all right? You can comment this out to return your to get back your max function, which uses the actual comparison, okay? But just to get the idea clear, you can specialize a different body just for a specific template. And for the rest of the templates, it will use the templatized version as shown here. Okay. Right. Moving on to class templates. The idea is similar. So we saw templates in context of functions, but we can templatize the complete class itself also. Okay. And very similar to templates, when you instantiate an object, okay, then only the compiled uh, all the things that we compile for a class actually gets compiled for templatized class. Okay. So because I'm in this case making an integer data type of max class, okay, the specific instance of this object with m, okay, the specific instance gets compiled. It's only just only with integers. Okay. You can do a implicit or explicit. So this one will be more explicit because we're actually mentioning the integer template, or you can go ahead and just do it, get away with the implicit method. Okay. So looking at in this example, we have a template T. Okay. Syntax goes something like this. You have the class max. So to templatize this class, again, you add on top of it that this is a template. Okay. And A and B are the member variables, each of data type T. Okay. The constructor, because it's the name of the name is of the function is the same as the class. So constructor T A T B. Okay. So A and B are the inputs, and it sets its own A and B. Okay. So hence I'm using this operator to access the pointer actually. And accessing the members A and B here, which are actually these members. The right hand side comes from the input. Okay. Next is yeah, actual max function where the body lies of the A greater than B and so on and so forth. So after constructing the object, I can call the max function as the dot using the dot operator. So dot max returns the max of the two numbers which were which are passed when constructing the object. Okay. Moving on. The next example, we have a more general class, let's say compare, and one can actually start writing more generic class where you use different operators. But here I'm just using functions to denote it. Okay. So the max function returns the max, main function returns the mean. Okay. It compares and returns B if because B will be less. Okay. If B is less. Very similar. We can extend the idea of this max templatized class to a compare templatized class where it can return both max and min. You can have more comparison operators. Okay. But again, just as an example. So we make the object, which is a class compare, passed two input parameters. So T itself deduces what is the data type. Okay. And then we can call max and min. All right. Looking at another example. Now the thing about templates is you are not exactly restricted to just using one template. That's what we have been seeing here. Okay. So as in capital T was the only template we used. You can move on and just use more templates. So we're using T1 and T2 to define two different data types of A and B. Okay. But another thing I'm ensuring is that the first data type is always returned. You can choose not to have this, as in you can have uh, different data type also returned, maybe something other than T1, T2. But nonetheless, I'm just going to use T1 for now as the rule. And yeah, the object one gets of compare class gets instantiated here. Okay. And after that, you can call the max and min function. You know the return type will be of whatever the data type of the first guy is. Okay. And when taking a few more examples, we can see the actual outputs. So let's say with some variations. So 1.5, 4.5, 2, 4.5, and 4.5 and 2. Can run this and check for yourself what is the output you expect and what is the output you are getting actually. Okay. They should clear things up. Okay. Another example is something like this, where let's say I have a templatized class, right? Or let's say A. I can make standard template library functions, which are templatized functions. Okay. As use the same data type as the templatized class. Okay. The nice thing will be I can just instantiate the class and the member also gets instantiated. Okay. So V, small v, is the object of data type standard vector, specifically of data type T, which we get from the class. So you can write things like this also. So you can pass like sort of a cascade your template across different classes, templatized class like this. Okay. You could have a different function which takes, let's say the body of the function takes or some other function, but a templatized function. You can use these templates or some kind of derivation of from this. Okay. To like maybe a if else kind of thing where if your template is of certain data type, then you want to use a certain template, you can play around with this. Okay. Essentially, the idea is that because this is compile time, you have a lot of things you can write, a lot of code you can switch around. Maybe it will work only for a certain template, not for the other. For the other, we want to use a different body in any of the function. Okay. So here, moving on. So public member init was made. Okay. so as to resize the V. So if we take pass some n, okay, so essentially we are resizing the private vector. Okay, the main function looks something like this. We define an object of a type, okay, specifically of integer data type. So we are using the template here, and objects in it we call as 10 because the init function resizes this internal vector, so it will resize it to 10 integers. Okay. And lastly, we saw about polymorphism, where let's say we have a base class B and it takes some init, okay, size n, not a problem. The extra thing we can then do is make a derived class, okay, but while the base class is not uh, templatized, yeah, the derived class we can make it templatized because of how hierarchy of pointers work in derived and base classes. You can use the same base class pointer for every derived templatized class you uh, again derive. Okay, so you can use a single base pointer which is not templatized, and that can act as a um, surrogate for your derived class. Okay, now in this particular example, we make the derived class D as templatized, as you can see, derived from the class B. The member is standard vector V, okay, and we have the init function, right? So we can make a B like this. Yeah. We can make the class B with the object name as small b and small d with integer templatized class D. You can write b equals to d also. We can make pointers and write the pointer D instantiate whichever you create as pointer b equals to d. Okay, and then use pointer b to call functions for every templatized derived class. That's also something you can do. But remember, you need the interface also to exist. So because init exists in both, okay, I can call this init and ask it to use the derived classes because this will override the already defined function inside the base class. Okay. So the good thing will be that if I wrote pointer b, okay, as some pointer to d, the specific instance, let's say d was instantiated with integer, that specific instance, and let's say a specific function is performing some kind of code for an integer data type, it is agnostic because we will call that function and automatically we know which version to actually call because we have instantiated with integer. Okay, so a lot of code can be abstracted out using these kind of concepts. So one of them is this polymorphism. Okay, right? Yeah. So we looked at a very important concept about templates and related ideas we can how we can extend from functions to classes and so on and so forth. Now today let's look at input output. So not just from the perspective of printing stuff like from terminal, so that will be the normal input and output, but also file IO where we are reading and writing to files. Okay, so how to do that in C++? Okay, let's take some examples. Okay, so let's first include iOS 2. Okay. So now the thing is, we have been using this header from the start, but yeah, now it's the time of it, it's time for it to shine. So particularly, we'll be talking more about how IO works. Okay. So IO stream has is as a header has certain commands. Okay, which we have seen before, and those are the ones which we will be focusing on. So let's take some examples. Main, main will have, let's say, integer a as a 5, double e as 3.14, and let's say integer c. That's it. Now, taking input from the terminal, okay, so we use something called cn. It goes something like this. So the syntax for it, okay, let me write another one and then I'll come back for it to contrast. So let's go with output as hello world. Okay, fine. This is something I've seen before. But notice something when you are trying for an input. Okay, so let's run this. Yeah, yeah. Let's first run this. Okay. Now, after running, it expects input. So I'll put 2 and just press enter. So when I press enter, I have registered my input to the terminal. Okay. So the interaction goes through terminal in this example, right? So 2 is the input which goes into C. Okay. This is the syntax for it. And for output, we are printing to the terminal this hello world, right? But let's go into more detail as in why this syntax. Okay, let's try to understand. Right. So standard CN, you can think of it like the terminal. Okay. Always remember your everything that happens is with respect to your code. Okay. Or you can think of it as the terminal also. Right. So standard CN is a terminal and it is using this operator to send the data to C. Okay. And if you think about standard cout as the terminal again, it's streaming hello world. Okay, and it is piping, okay, as in queuing also standard ENDL as an extra line, right? So first to the terminal, hello world gets streamed, okay? So this string of data gets streamed to the terminal, and furthermore, a standard ENDL where the end line gets streamed, okay? Another question for you guys, where have you seen this operator before? Double arrows, double angular brackets, so on and so forth.
A right shift operator.
Yes, that's correct. And one might wonder what does even shift operators, like the bit shift operators, right shift and left shift, are doing here, right? It's actually um, not so unrelated. By that I mean is when you're using this shift operation, you're actually in a way streaming the bits. Okay, so this is overloaded operator for the shift operation for these functions. Okay, so the C in and C out are, well, these are also functions. They don't look like one, but well, take my word for it. They're also functions. but not in a general sense that you have brackets taking inputs and all. This is for these cases, the operator is this guy itself, where you can chain a lot of strings. So you can chain with first this guy, the first left shift operator as sorry, first left shift operator as the first hello world, then also Q using the same operator as standard ENDL. And you can keep going, okay? And because and to provide this kind of functionality, the standard is written in that way, okay? And yeah, so this shift operator, okay, essentially streams the bits of whatever you are um, passing, okay, to the terminal. So in a sense, this is a overloaded shift operation, okay, but streaming the bits. Now, the picture about Cout and Cin being terminals also should be more clear. So we are streaming hello world and also the function ENDL to the terminal. And from the terminal, we are streaming the bits to our internal variable integer C, which is part of the program. Okay. Yeah, another thing, slight detail, but well, the same thing you can achieve by using the slash n. Okay. So ENDL does end the line, as in after the end, it inserts a new line. In particular, you can use slash n to insert new line. Okay. But there's an extra thing that standard ENDL does is that yeah, is that it not just enters this thing, okay, a new line, but also clears the buffer. So remember, when you are streaming all these bits in a queue, right? So you have this portion which is will be in the queue, this portion also, and then maybe you can chain it with multiple inputs. So this queue, right, gets stored inside a buffer. And what ENDL makes sure of is that when this is called, that buffer gets cleared and your actual output gets printed. Okay. Now, why do we have this buffer? Is the reason is more on optimization. So it depends on the OS when it wants to which path your inputs and outputs should take as to when should I clear the buffer, right? So managing all those things is done by the in default is done by the OS, but you can actually force it to flush your data. Okay, so this is the flushing of the buffer. So ENDL inbuilt takes care of that. So in particular, you can think of it this way. So standard ENDL is standard flush. So you can actually use standard flush here also to ensure that you get your um, buffer buffer clear. So the output will appear. Okay, and plus slash n. Okay, right.
So is there any limit on the size of the buffer?
There should be a internal limit. I'm not sure. I guess it should depend on the operating system. Again, hardware implementation and so on and so forth. But it's like stack. You have some limit on that. So yeah, there's an internal limit on that buffer. Again, depends how much your OS decides. But maybe that can be changed. I'm not sure if that can be changed in a standard ISO C++ has any command for it. But yeah, there should be some commands outside the code in the OS level. You can probably put some environment variable or something and then change that. Yeah, in
So,
general,
so there will be some unintended behavior if we do not usually use this standard ENDL after maybe some printing also.
yeah, correct. The intended behavior would be that you want the sequence of printing should be in a certain order that will be respected if you're in a serial code. If you're not in a serial code, right? So let's say you have a parallelized code where two threads, okay, are printing the same thing, but maybe they have a certain data extra line that they're also printing their thread ID. Okay. And there's a lot of string. Let's say that this is just a few lines of code, but let's say there are a lot of strings. It is possible that they will be sequential for their own context, as in a single thread will be having sequential write outs, okay, something like this, and the second thread will have its own sequence, but the actual thing that you're saying can differ, right? Um, because it's possible that they're using the same buffer or they have different buffers. It really depends. So it's sometimes easier to just clear the flush because maybe at let's say you're debugging something. Maybe at this point, I want all the print statements to be printed and for my thread to move to the next sequence. So yeah, unintended behavior, yes, you can have. The case I gave as an example is a very particular case, but maybe you can find some other cases. But in uh, distributed computing or like parallel programming type stuff where you're using threads and processes, MPI and all, you can run into issues like this, where you're printing debug statements, but the buffer has not been cleared. So it's not filled yet. So the flushing of those buffer as for the statements is not being done in a proper sequence that you expect. Yeah.
So is it because we are implementing it in a cascade manner? Right, this doesn't cause a problem in C. Since we are here implementing it in a cascade form, that's why we need to flush, or it is different from how C handles or C++ handles.
No, the way like from top to bottom approach, it is pretty much every C-like language does that. So that is let's think that's how we'll be coding it always. Okay. But one thing I have to remember here is it is a property of the buffer itself. So if the buffer does not get filled, it usually does not evict it. So the print statements might come out of order, especially which is especially true if you have um, multiple tasks or threads. That's it. That's all.
Okay.
As such, if you have a serial code going from top to down, top to bottom, the order in which the queue it does is the order in which you actually did the code. So first this and then this and then this and then this like that. It's just that when you when do you actually like what order do you see the actual output might differ with what you're actually putting, depending on if some other thread is also putting its queue. Yep.
Suppose we have a normal scenario where we are not having multiple threads running. It's just that there are different files, like 10 of files, and I am using just standard cout and I am nowhere doing standard ENDL. In that case, what will happen? So that
So,
was my question.
okay. So in that case, it's possible that you will get your output in chunks. That's very likely the situation. The chunk will be the buffer size.
Okay.
Yeah. And then the second line you read a certain like you just keep streaming with um, line by line every file. Okay. So once the buffer gets filled, then only you get a certain chunk of data, and then the next chunk. That's how. In general, if you have serial code, sequential code like this, you should not see any difference in the order of outputs, generally speaking. Yeah. The idea about buffer being filling and all mostly comes into play, I would say, during only multi-threading. Yeah. Because let's say your thread in this region, uh, was printing something by one thread and second thread, it's possible that your thread just ends without letting it print something of the region, something like that. So to make sure that everybody has flushed like whatever output they want, standard ENDL is very useful. That's what I'm saying. Yeah. Okay. Any other question, or is that not clear?
That's fine. Thank you.
So taking more examples, we can also just print A. So this is something we have seen before. So simple printing all the variables. Now, another thing to remember is this is a string, right? So this shift operator is overloaded for strings and also overloaded to accept its own functions. Okay. So just from seeing from how syntax wise, this is a uh, m- quite nice interface. I mean, well, maybe could have been done also some more changes, but then again, this because of overloading a lot of inbuilt data types and other things, we can just keep chaining using the shift operator. Okay. And the direction of this operator gives an idea as to what is getting queued where. Here it's a string. Also, we can overload with an integer, right? We can overload with string again and with a double string again, C, and with another integer. All right. So printing, oh, my bad. Is the double. Yeah, it expects an input, so 4. Yeah, and then prints the rest of them. We can just make it B. Okay. All right. Let's take another example. I'll include the IO stream as usual. Main function. Define integer I as 70. Then a long L, which is, let's say this guy. Okay. And a long unsigned integer. We call it I64. So it's a 64-bit integer, as in the largest integer you can represent. Okay. So that's the data type of it. And yeah, that is something like this. So it's in hex representation. Normally, whatever your like numbers you write, they're in decimal. Like that's the default behavior. But nothing stops you from writing numbers in hex also. So the way to distinguish is you start with 0x. Okay. So if you write it 0x, so it means that from there on, all the digits that you are going to encounter are in hex format. Okay. Now, another float we can define, which is let's say 15.0 divided by 7. Very similarly, let's define double also, which is also doing the same thing. There's a reason I chose not completely divisible numbers. So to represent the actual digits, right? So let's look at that. And let's define character C as X. Maybe I'll guess this. Yeah. I can make it const character also. Let's call it pointer S, which basically means it's here the character just was storing a single character. Okay, letter. You can think that way. But here it's a it's actually stores a string. Okay, so something like hello world. Okay, I can also make um, store the address of S. So something like this. Unsigned integer address of S as long unsigned typecasted integer pointer, of course, because this was character pointer, right? So I have to typecast it, and yes, it was const. So again, you have to typecast it. Yes. And yeah, one more. Can do the addressing even for the integer I that we had defined before. So let's say pointer P is storing the address of I. Yeah. Now let's use these pieces to print a lot of stuff. And let's see out I that will have outside. Right. So I'm printing I, and yeah, that's it. And for now, let's just go with that. So it prints 17. It stores 17 in decimal form and also prints it. Straightforward. This is what we have been seeing previously. This time, let's write the same thing, but in the hex form. The hex form of I, okay? So what we want to do is use the hex function in standard header file, standard table library. So I put it in hex form. Let's compile this. That is 11. Okay. As in, if you take I, which is 17, in hex format, it will actually be 11. Okay. In decimal, the same number, which is 17, in hex becomes 11. So in C++, you have the option to convert your numbers. Okay. By default, they actually print hex, decimal, but you can ask them to print the hex formats also. Okay. You can even print other formats like opt. So let's do that. Opt I. Same number I, but we're also printing in the opt format. So let's do that. Here's 21. Okay. Same number 17 in decimal. It's 11 in hex and 21 in opt. Okay. Or maybe I should not call it 21, 21. Yeah. It's 1 in hex and 2 in opt. Right. So yeah. Let's print another one, which is yeah, L. What do you guys think will have be printed now? Okay, let's go ahead and do it. So it prints a large number. Okay, and what you notice is this, it did not print exactly this thing, right? It printed something else. The reason for that is while we say to this L to store this particular number, which is given to be in hex. Okay. End of the day, when it is stored, it is in zeros and ones, right? You have to always remember in this classical computing, okay, whatever computers you are dealing with, numbers are stored in zeros and ones, right? So end of the day, this also is stored in zeros and ones. The default behavior of printing will be in decimal. Okay. So the same number, which is in hex, when converted to decimal, will provide you this number. Okay. You can take it further. So maybe ask it to print in hex actually. So what we did here. And then you see as the actual number that we provided 12A, 12A, 78CV, 12A, 78CV. Okay. The like I said before, 0x just indicates that this is a hex number. Okay. Not some decimal number or anything as such. Okay. Very similarly, we can also print other numbers, which is the I64 or I is like the 64-bit I. So hence I'm just calling it I64. So if I go ahead and just print this too, right? So again, you see a very large number. Oh yeah, my bad. Because I made it as hex. So yeah, it is actually printing the hex version also. So let me just run this one now. Yeah. So it's actually printing the actual decimal version. Okay. All right. Just to check, again, one can make it hex again to print this in the hex format. Yeah. Okay. Now let's print a very important aspect. So let's print. So after this, these two guys, F and D. So let's print F. Yeah. Okay. Similarly, let's print D2. Let's see the output. Okay. So if you see here in this case, so 15 divided by 7, it is not a perfect divisible number, right? So if one thinks in terms of decimals, okay, so it's a rational number with non-terminating bits, non-terminating decimals. If you think about it, the decimals that you are able to represent, again, this is actually, it will take infinite precision. But since we have limited sizes for float and double to represent this number accurately, there should be a difference between how float would store this number and how double would store this number, right? I guess everybody will agree on that. And because double is higher size, so it's 64 bits and float is 32 bits, you can expect double to store this same number more accurately. Okay. All right. Now, just so happens that when you're printing this number, it is only printing till 5 digits, right? So 14286. And we're not able to see the distinction as to is it actually storing that much number? Okay. Like, to what digit is it actually storing? So what in this case you can do is, let me write a header. So I had precision. All right. So particularly for this, we can use a function called standard precision. Okay. And then you can give how much, oh, sorry, not just precision, you have to say set precision. Okay. And this you can tell how many extra decimals you want to print. Okay. Right. So there, after this, if you just print f and t, you should be able to see more represented decimals. Normally, the default in general is, as you can see, like 4 or 5 bits. So you can increase the precision of your. So it's not that it only stores till 6, like 14286. It's just that by default, when you print it, it won't show more decimals. Okay, more precise digits. That's the only thing. Okay. Right. So to actually see those bits, we have to increase the precision. All right, my bad. It actually requires an extra header file. So you have to include that too. So it's IO manipulation. So IO manip. You have to include this header file to access this function. Okay. Yeah, as we see before. Oh, my bad. I did not actually put the fng. All right. Let's go. Yeah. So if you see here, so 15 divided by 7 is indeed 14286. But for F and D, if you print the rest of the digits, as you can see, it is 5. 86 was rounded off, right? More precisely, it's not 86, it's 85. Okay. And then 7. And then next digit, if you compare, here it is 0, it is 1. So yeah, this is the limitation of floats. They can only represent up to like till 6 decimals. Yeah. But double can represent more, okay, higher bits. So it's not like double here, which is D, has infinite precision. You cannot trust all the digits here again, but you can be rest assured that the digits in you can trust are more in D than in F. Okay, that's sort of the idea. Okay, now yeah, like I said before, it's difficult to make out how many decimals you actually don't need to print it always. So hence it gives a shorthand uh, precise bits of whatever it's underlying it is storing. Okay. But rest assured, it actually stores the 32-bit representation of whatever this number is for F float, and for double the 64-bit version. Now, while doing the arithmetic, it will use those bits, okay, accurately and all, and so on and so forth. But while printing, you have to do some manipulation to get those higher bits. Okay, that's what I'm saying. In general, you don't see all the bits because that's the default behavior. Okay. Now let's print more values. So let's print C. Okay. So if I print C, it prints X because that's what we stored here. So character, so C is a character, it stores X. And if I want to print C, I can just put that character and just print it. Again, this is overloaded for characters also, right? Yeah, so not a problem. What if I want to print the variable S also? So S, and it's a question. When is typecasting required? Either we always use a bigger storing type. Okay, so if you want to be on the safe side, and let's say you're doing a lot of arithmetics, and again, precision always comes first in more or less a lot of cases. So if you want to be on the safer side, you can always go with a higher data type. Let's say you use FP64 double always. Okay. So more or less, you can be rest assured that is good enough for my most of the cases. But it is possible that you might want to use a lower data type. There are a lot of performance perspective because you're losing precision, yes. But what you gain is actually on performance, where your calculations will be much, much faster because the hardware that does double and the hardware that does float, you can think of it like, because it is 64-bit versus 32-bit, you can process more data at the same in the same time. Okay. That's the short of it. So what you gain is actually performance. So um, if your code or any portion of your whole algorithm is okay with shorter or less precise data, like let's say it is good, if float is good enough, then to get answers faster, you can use just float, or else you can accordingly do it, yes. But do remember, if a float was already less precise, converting into double does not make it more precise. As in, let's say, uh, out of those 32 bits, okay, those are precise, yes. But when you convert them to 64, it's not like magically you gain more precision. You don't. Those rest of the bits are something, but they don't provide the more accuracy. Yeah, depends on data. Yes. In general, typecasting is very useful. So you can do it um, depending on where you're converting. Yeah. So cases like this, yeah, cases like this, I would say you can use static or dynamic casting if you know those are they're compatible data types. So you can use uh, those type of casting. Yeah. Okay. Let's print this too. Right. So when trying to print S, right? Yes, it's a character pointer, but there is a sort of a null termination, okay, to S. So it knows that your, like, how does it know how many characters to print, right? So it will print till the null termination. By that I mean, when you have the string hello world, okay, with the exclamation mark, after that there is a termination point which is entered, okay, to say that, oh, this is my S pointer starting from this character until this character, it actually owns it. Okay. So yeah, your overloaded operator um, notices that and only prints still that character, the exclamation mark. Okay. Yeah. We can also, because it's a pointer, let's print its address. So yeah, this is the address of the S pointer. Now, you remember we also typecasted that address, right? So this is the S, and we typecasted that address to another pointer, right? So let's print that too. Address of S. Okay. It's a different value, as in it's the interpretation is different now because we changed we sort of typecasted it, right? So the value is now whatever address is storing, right? Okay. You can also typecast and print the void type. So let's say it is void enter. Yes. Printing this. Yeah, they give the same answer. Okay. Yeah. Finally, we can just print the P that we use, the pointers pointing to I. So that will be here. Now, let's see. So that is the address of I. Okay. All right. Okay. Let's take another example. This next example can be a little confusing, but let's go bit by bit and like in pieces and then try to understand this. Okay. So as usual, I was stream. Then I'll have a class called complex. Okay. This is something we used while starting the discussion on classes. The same complex class has members real and imaginary. Okay. So let's write those. So I'll make them as double. So re is the real part, I am is the imaginary part. Yeah. Simple. And let's make the public portion of it, which is complex, takes double, then underscore re, double, underscore imaginary, and then sets re using underscore re, imaginary using underscore in, and the body, I'll just leave it empty. Okay, that's it for now. Now make integer the main function. I'll define the complex number C. Let's define two numbers, C1. Let's say this is 4.7 and 8.9. C2 as 3.9 and 4. Not 4, 7.6. Yes. Okay. Now, previously, to print this number, we had to access the members and print them individually. Like, let's say I had to do something like this. Real part, and then you access the real part from C1, right? And imaginary part, let's say, and imaginary, so on and so forth. Okay, for C1 also, yeah. Right. But there's a small downside here. These are private members, and you have to write getter functions. So let's say I don't want to change the access specification. So I want to still keep this as private and not make it public so that yeah, I don't want to make it public. So code like this won't work, right? So you have to write getter functions. But is there another way? So there is another way also. What you can then do is, okay, so we basically want to keep this simple so that this overloading, while in general it cannot know the complete um, complex number. By that I mean is what you have seen before in all these examples. This, okay, just give me a second. Yeah. So what I'm saying is you have this string and your shift operator knows, because it's overloaded, how to print strings, characters, inbuilt data types like integer, double, and all. Okay. So it knows how to deal with them. And we took different examples here. So it knows float and double, everything. But what about custom data types? Of course, it cannot know them, right? Because this is something we made it. But can we do something like this still? So the goal is, say I want to just put C1, C2. Right. That is the motivation. So even if the object is not known to the output, okay, can we still do something like this and get my real and imaginary parts printed of my complex number? So that is the goal. Okay. So let's look at how to do the same thing. One was to actually explicitly write each part, because the real part and imaginary part individually are double. So your operator, shift operator, recognizes them. Okay. But something like this, it won't. So, I mean, I'll just compile and show you the error anyway. So, yeah. So it'll get a lot of errors like this. Okay. Yeah, if I comment this guy also, then everything is good. Right. Okay. So this is something we want to achieve. Right. So to do that, we'll take example of friend function. So remember, friend functions are functions which you could write the definition outside the class, and the function itself has access to the all the member variables, even the private member ones. So let's write a friend function whose data type is standard O string, as an output string. Okay. So this is the data type. Okay. And the return is actually a reference. Okay. So ampersand. And we're using the specific operator, this guy. So operator, to say that I'm trying to define this left shift operator, the double angular bracket, and defining a sort of overload actually. Okay, you can think like this is an overload. So, so to say that I'm actually trying to change this operator, I have to use the keyword operator. This is the data type. Okay, it returns a reference and it's a print function. Now comes the input. So the input itself is also of the data type O string. So for the data type, right, O string, and again needs to be reference because we don't want copies. We'll be clear why we don't want copies. And let's say OS is the object, which is the output stream. Okay. Furthermore, we'll have a const, right, which takes complex reference to C itself. Okay. It takes a complex number and the output stream. Okay. And it returns a output stream. You can sort of feel what we are trying to do here also, right? So there is a complex number, okay, which itself is a part of a stream, right? And it is returning a stream to this guy. Because this can work with even C2, because till here there was a stream, right? So for C2, it needs to have a complex number with the whatever stream we already were providing and just queue it. Let's see how we do that. Now comes the body. So standard C out, okay, right? Where I want this part, okay, and then C dot real, okay, and then I want the comma. So basically I want to print the complex number in this bracket format. So that, and then C dot imaginary, and then end the bracket. And end the function. Okay, so this puts it inside the stream, okay, and you just return the string OS. That's it. You take the string, okay, you put it, you queue this thing itself, right? Start with a standard cout and then return it back. Okay. This is, yeah, I'll just on this. Okay. Now, because of writing it in this format, I can actually enter one more. Yeah. This is something we're interested in. Okay. So yeah, now let's print this. Okay. Interesting, right? So now you're able to print the complex number 4.7, in this format. So you use the brackets and internally it uses the real and imaginary with a comma separation. Okay, like this here. And this comma is something I just used to separate the complex numbers. You could use semicolon also, not a problem. So as to see where the actual comma is coming from. So this semicolon is coming here, and C2 is printed like this. So 3.9, 7.6 with its own brackets and comma separation. Okay. So what is actually happening is your operator, this guy, okay, when we are putting it in with all these values, is essentially taking the stream, okay, but is also taking the complex number, because you have to remember the way this whole standard C out, C in, and all these things are written is there is a stream, okay, and it has its own data type. That is a standard out. Okay. Now that stream we are updating with another line, okay, so that that can also work with whatever we want to desire when we have complex numbers. Okay, particularly the user defined class complex. More particularly, it will print the imaginary and real part in this format. And finally, it returns the string. Okay. The syntax might look a little daunting at first, but once you break it down, I think you can understand it. It's not difficult, just that each piece has its own role. You just have to understand that. Okay. Any questions?
Sir, why the return by reference is required?
Yeah, because if you think about it, you can update the actual thing, but if you don't, okay, if you don't return the reference, it might return a copy. And if you remember when I talked about copy and references, like when I talked about references, it should be yeah, yeah, something like this. So you might create the B vector, and if you return it, uh, return a copy of it, that is not something you might want. You want the actual changed structure. So for example, yeah, here I had A, I had C2. Okay. But if I want to set A, I want my actual A to get set, not some internal vector that was created and then destroyed. Right. So that's why we use references here. When you're saying reference, we want to preserve, in this case, whatever the actual stream was. We are you can think of it this way. We are adding more to this output stream. Okay. Using the standard cout, you are adding more to the stream, and this updated stream is what you want to return, because the operator, the function that you're calling is actually this guy. So yeah, this guy, particularly here also, but this is a different, not this function will get called. This is some, this is for the string. Here in this case, it will be called for C2 again. Okay. It's a little confusing format because uh, functions with this kind of syntax are not usually written, but rest assured, this is also a function. Actually, another thing, you might have seen the uh, yes, I define standard vector, right? So let's say standard vector b as 10 something, and it has values or whatever, and I write a for loop as something. Now this for loop, we also write v bracket I, right? So very exactly, this square bracket is defined like this. So use operator square bracket, and maybe just write this square bracket, and in the body return v dot data plus I, is plus I, whole dereferenced. So you do the pointer arithmetic and then dereference it. So yeah, it takes I, yeah, it looks something like this. So the bracket operation is also this guy actually. So use the operator keyword to say that I'm defining this operator. Okay. Takes input parameters I. Yes, it does. And yeah, the return looks something like this. This is sort of the syntax that one goes with. Okay. Right. Okay. Uh, More examples. So as I assume, include the I string main function. Yeah. In this example, we will, yeah, we'll include another header file, which is called f-string. More particularly, this is for file streams. Okay. So f-stream has different data types. So one is OF stream. So as in output file stream. Let me call it my file. And my file, I will use the function open. So it will open that file. Let's call it test.txt. And then my file, I will write some text to it. So let's say first I'll write hello world. Okay. And new line. Then my file, value 1, also new line. Two, new line. And just, yeah, look at 3, 4, 5, 6, and let's say 7. Okay. Values ended. And finally, I'll just fill it, let's say with test and the line. End the line. Okay. Now finally, because I opened the file, good practice. So let's close it. Okay. That's it. before, if I try to print, okay. Now it is done. If you see here, test.txt was created. And if I open that file, all the test inputs that I gave is actually printed. And the last line also inserts a new line. Okay. So this is output as in output from your code. Okay. So you can think of reference as in always your terminal, or like you can think from terminal to terminal. Okay. Here in particular case, and there also you can do this. Think your everything is a reference to your code. So from your code, you are outputting. So you're using the output stream. Okay. You open the file, and if it does not exist, it creates it. Okay. Then my file, you're streaming all this data. Okay. To the stream. So hello world first, then the numbers, and then the final test text. Okay. After all this, okay, after everything is written to my file, let me close the file. Okay. Right. Now, very similar to that, since we have written to a file, now let's read from it too. To the F file stream, include IO stream. Let's also sorry, let's also include the string header. So main, then standard IF string. So input file string. Also call it my file. In this example, I'll take the same file test.txt and the line. Then I'll define a string called line. So essentially the idea is that every line that I read from that file will be stored in this line string. Okay. Then let's run this. While can use the getLine function. Okay. My file and line. Oh, the reading from my file, storing it to line. Okay. Until so this keeps going until you reach the end of the file. So at each step, you are printing the line. That's it. No, that is for this creates the file. Yeah. So it actually reads those files, right? So the 5 reads from text.txt and prints all those lines. Okay. So let's say I delete all of this. Okay. And after text, I add 100, 1000, and some other large numbers. Just to show you guys, this is the actual file it reads, not from output 4 or something. So now if I run 5, it prints the new updated data. Okay. So to show this, I just updated the actual file itself that is reading, and you see the updated data. Okay. So this is file streams, both the output file stream and the input file stream, where you can read line by line until it reaches the end of file, in which case the while loop ends. Okay. Right. Okay. Another important thing to do is you should put guards to check if your file is actually open. So if it is not open, then you go ahead and uh, perform this reading. Okay. And yeah, because if it is opened by some other file, it's possible it is getting overwritten. So it's good practice to always see if the file is not open and then open it and perform all that read or write and then close the file. Ideally, if the file is not being written to, multiple handles can actually read from it. That's not an issue. You don't get race conditions. But yeah, if it's being written to, then you have to be careful. Okay, right. So yeah, that's all for today's session. If you guys have any questions, I'll be here for few minutes and feel free to ask me. Else, we'll see you guys next week and we'll be covering topics like auto and decal type and type IDs. So those will be the topics for next week. Okay. Thank you and see you guys next week. Yeah. Yeah, thank you. Thank you. Hope you guys enjoyed it. Yeah, thank you.